Hello, this is Tucker from the Math and Physics Resource Center at SVSU, and in this video we're going to go over another hypothesis testing example, this time with a two-tailed test. So just getting into the example here, we've got that a neurologist is testing a new drug that allegedly changes the response time in rats. Through a sampled test, the neurologist administered the drug to 16 rats, who resulted in a mean response time of 96 milliseconds. If the population mean response time is 94 milliseconds with a standard deviation of 4, is there evidence that the drug has an effect on response time? Notice that here it doesn't specify a negative or a positive effect, it's just asking us to see if it changed. So that's where the real crux of the problem comes into play here, because with our hypotheses, our null and our claim, we're going to have to test whether it's equal to the mean or not whether it's greater than or less than. So first let's just pull the info out like we usually do. So we've got 16 rats, so our n is 16. The mean response time of the sample, x bar, is 96. The population mean response time is 94, so our mu is equal to 94. And our standard deviation is 4. And it's telling us that we're using alpha of 0.05, but we'll get into that a little bit later here. So our null hypothesis, since we're testing to see if the drug has any effect, positive or negative, in this case we're testing to see if mu is equal to, in this case it's 94. Now for the claim, since we want to see if it has either positive or negative response, we can just say that mu is not equal to 94. So because of these hypotheses, we have to accommodate for that in our rejection region. So an alpha of 0.05, usually with a rough, that's kind of a normal curve, with a rough normal curve here, usually we'll just have one tail, where like this shaded in area is equal to 0.05. But since we're using a total area of 0.05 for a two-tailed test, because technically we can reject over here or over here, we have to split that area between these two. So if our total area has to be 0.05, we can take that alpha, divide it by 2, and just assign it to each of these tails. So the area here should be 0.025, and the same with this one, 0.025. So whenever we have a two-tailed test, just take that alpha, divide it by 2, and we'll be testing for that on both sides. So from here, I'm going to do this problem with the z method from the last video. So we can take these areas, the 0.025, and find their corresponding z's for the rejection region. So once again, if we take this, we'll subtract it from 1 to find the area that our z corresponds to on the table. So this will be 0.975. So we're going to be looking for 0.975 on the table here, which it comes up right here, 0.975, which is 1.96. So our z of alpha divided by 2 is 1.96. Now, to get the left-hand rejection region, we could either find this 0.025 on the table, or because the normal curve is symmetrical, we can just say that the negative z alpha divided by 2 is just negative 1.96. I know that's kind of hard to see, that's supposed to be a negative 1 there. Negative 1.96. So I'll just redraw the normal curve down here. Kinda. So the z values that we just found, negative 1.96 and 1.96, and we'll call this one the mean. we have to figure out if our sample is less than negative 1.96 or greater than 1.96 in its z-value. So let's figure that out. To find the z-value here, remember that it's x bar minus mu all over the standard deviation divided by the square root of n. So if we plug in all our numbers, we'll get 96 minus 94 all over 4 divided by the square root of 16. Which, if we simplify that down a bit, we get 2 over 1, which is just 2. So our z for this sample is positive 2. Now remember, we're going to take that and compare it with the z alpha divided by 2's that we have here. So this one is z alpha divided by 2, this one's negative z alpha divided by 2. And now remember, to reject, in order to reject, we need our z to be either greater than z alpha divided by 2, or we need our z to be less than the negative z alpha divided by 2. So if we kind of just plug in our z to this, we've got 2 is greater than 1.96, which this is true. So because this is true, we can reject the null hypothesis. Now, once we've determined that we reject it, we want to write a little statement to show what this really means. So what this rejection is telling us is that there is significant evidence to show that there is a difference in reaction times between, we'll call them drugged rats or not drugged rats. So we just want to kind of clarify in the context of the problem what this rejection really means for us. Because our null was that there is no change in response time, this means if we reject it, there is a change in response time. So, like the last problem, I can also go over the p-value method, where our p-value in this case is this 0.025. Remember, since we split up the 0.05, our p-value has to be this one. So the other way of solving this, once we get this z equals 2, so our z is 2, our alpha equals 0.05, and our alpha divided by 2 equals 0.025. Now we want our p-value, this is 0.025 here, and so is this. Now notice, with the p-value method, neither of these sides are negative because we're still dealing with the amount of area under the curve. Since our area above the line here can't be negative, both of these are still going to be positive. So in order to reject, we need to find if our p-value is less than 0.025. Now to find our p-value, we'll take our z equals 2, and we'll find the corresponding area here. So we have 2.0 is 0.97725. So z equals 2 means 0.97725. And we'll take that, subtract it from 1 to get our p. So our p in this case is 0.2275. And now we'll compare that with our rejection region. So if we take that, 0.02275, that needs to be less than 0.025, and this is true. So once again, we'll still reject the null hypothesis. And if you make it to this point with this method, you'll still want to do this kind of explanation after the fact. So that's about it. Thank you for watching.